All right, so let me just do the Hamiltonian formulation very quickly. Okay, so the good thing about the Hamiltonian formulation is that all the equations are first order. But as a result, the number of equations you deal with is twice as many as that in the Lagrangian formulation. Okay? So this is the Hamiltonian formulation. So we start with the Lagrangian. Again, we take just one particle. So I'm switching from x to q. Now we define first the momentum that is canonically conjugate to q. As you can see that classical physics was really formulated by conservative Christian men, canonical conjugate. So the momentum is defined to be P is given by del L by del Q dot. So this is the definition of the momentum that is canonically conjugate to Q. So we can check for Newton's law, this gives us the correct momentum. So for Newtonian physics, L is half mx double dot minus double dot x squared minus v of x. So del L by del x dot is going to give me mx dot, which is exactly what we call momentum. So yeah, so this is a good definition. Okay, so then the Hamiltonian H is defined by the Lagrangian minus P times Q dot. And if we have more than 1 degrees of freedom, then the Hamiltonian is given by the Lagrangian minus the sum over all the degrees of freedom with Pi Qi dot. Okay. Now remember that the Lagrangian was a function of Q and Q dot. Let me just switch to multiple particles. So I'll just put an index here. Then this transformation is what is called a, do people know what this transformation is called?
Legendre transformation.
The Legendre transformation. And those of you who have done my StatMech course, there was a tutorial dedicated to how the Legendre transformation changes the functional form, right? So what will happen is that the Legendre transformation would replace the Q dot dependence of L by a P dependence in H. So as a result of the Legendre transformation, we'll get a Hamiltonian function, which is now a function of Qi and Pi. Okay. So if you want to review Legendre transformation, I encourage you to go back and look at the tutorial. But if you haven't done that course and you want to look at it by yourself, you can email me or send me a message and I will share the tutorial with you. But I will not spend time on the Legendre transformation here. Okay. So what are the equations of motion in terms of the Hamiltonian? So let's just first take the Euler-Lagrange equation and replace the Lagrangian by the Hamiltonian. Okay, so we have Euler-Lagrange equation, d dt del L by del Qi dot minus del L by del Qi 0. I've just exchanged the terms here. see that this guy is nothing but the canonically conjugate momentum. So I get d by dt of pi. And this is equal to, and take this to the other side, this is del by del qi h plus sum over, say, j, pj, qj dot. So now, see that we are taking the derivative with respect to q, but q is not here. It's only p and q dot. So this is going to go to 0. So I'm going to be given by delta h by delta qi. So the first set of Hamilton's equation is pi dot, the time derivative of the momentum is given by the partial derivative of the Hamiltonian in terms of with respect to the generalized coordinate. Okay, so this is the first set of Hamilton's equation, and because it's formulated in terms of p, this is a first order differential equation. So we need another set, and the other set of differential equation is easily derived from, if I take the Hamiltonian and take its derivative with respect to p, then I just get q of I. Okay, so this is just so this is the other set of, sorry, there's a qi dot, sorry. Okay. So these are the Hamilton's equations, okay?
So how did the second one come about, like from the Euler
if I look at H, what is H? H is this thing, right? And if I take with respect to pi, then it's going to give, kill this guy, and what I have left over is minus q dot. Okay. So, okay. So the comment, so, in the next class, I'm going to talk about the Poisson bracket, but before that, let me make some comments. So Hamilton's equations are first order in time. Number two, they treat position and momenta on equal footing. See, they look very similar. And number three is that, Hamilton's equation, motivates the idea of a phase space. So phase space is a space in which the axes are the generalized coordinate and the generalized momentum. So that means that a given point in phase space completely determines the configuration of a system at a given time. So the evolution of the system is then completely given by a path in phase space. Okay? So for example, if I look at the phase space of a simple harmonic oscillator, we know that the paths have to be circular, elliptical, where the size of the ellipse depends on the energy. Another thing about phase space is that two paths in phase space can never cross. Because if I start from this point and suppose that the path crossed and this was a real crossing, then of course that would create the ambiguity, because then if I start from this point, does it go here or does it go here? We don't know. So paths in phase space cannot intersect. Another important idea, so this was 3, is the idea of a Poisson bracket. So if I have two, say, observables, say, physical quantity which are functions of Pi and Qi, say A and B, then we can define their Poisson bracket, and it's given by dA by dQi. There's a sum over I, dB, dPi. So there's a sum over I minus dB, dQi, dA, and dPi. Okay, so this is known as the Poisson bracket. And if I compute the Poisson bracket of Pi and Qj, what do I get? I get, the second term would be 0. So the first term is going to give me delta ij, right? And in terms of, you can even express the Hamilton's equation, which is Q dot, as the Poisson bracket with H and Q, and P dot as the Poisson bracket of H and P. Okay? And so what these Poisson brackets is that they give you a geometric interpretation of the phase space. What do you mean by that? Suppose that you have some n-dimensional system and you have a phase space, but you have, say, the possibility of choosing two Hamiltonians, which which can govern the same degrees of freedom. So that means that if you start with the initial point, one of the Hamiltonian will say take you here, but if you had a different Hamiltonian, it'll take you somewhere else, right? So that means that the Hamiltonian, the specification of the Hamiltonian function, what it does is that it provides a vector field on phase space. So, choosing a Hamiltonian is equivalent to choosing a vector field on phase space. And if you chose a different Hamiltonian, you would have a different vector space on your phase space. Okay. So that if you started, say, with this point, with the red Hamiltonian, you would move in this direction. But if you started, say, here with the green Hamiltonian, the blue Hamiltonian, you would move in this direction, right? So, I just wanted to introduce you to the idea of phase space because of Poisson bracket, because there is the formulation of quantum mechanics according to Heisenberg can be described in terms of a prescription that Dirac gave of replacing the Poisson bracket by the commutator. Remember that in quantum mechanics, so I think there should be a minus sign here, yeah. In quantum mechanics, the fundamental commutation relationship is position in momentum, Qi Pj will give you I, h bar, delta ij, right? So So what Dirac said that if you have a classical mechanics system and you know Hamilton's equation, the way to get the quantum mechanical counterpart is that you take the Poisson bracket and replace it by the operators times in a commutator divided by IH bar, and you're done. So that is the Dirac quantization condition, or Dirac quantization rule, I should say. Okay, so anyway, I think I'm going to stop here. And in next time, I'm going to talk about path integrals. Any questions?
Sir. Oh, so having QI and PI on equal footing, like what kind of advantage does this give us in terms of the physical or mathematical stuff?
Oh, many advantages. I mean, so for example, suppose you have formulated your Hamilton's equation, and you found that there is, when you look at it in this direction, you see that PI and QI, as naturally suggested by the formulation of the problem, is not the one that's going to help you solve, say, the system. So you can actually transform QI and PI without changing the form of the Hamiltonian equation, and those things are known as canonical transformation. So you have access to an infinite number of a large number of transformation, so that you can play with the Hamilton's equation, and the differential equations can be put in a form that's more amenable. And then also too, for discussion about if general evolution of system, integrability, ideas about chaos. So for example, you can say that the formulation of the notion of chaos could be that suppose you start with 2 points which are infinitesimally close to each other in phase space, but under Hamiltonian flow, in given time, if they diverge exponentially, then those systems are what you would call chaotic, right? So yeah, I mean, it just gives you a very powerful, insight into classical mechanics, and also gives you a prescription into quantizing any given classical system. Okay.
Yeah, I need to properly study this thing. I haven't
Yeah,
done.
I mean, I'll give you some examples in the next classes.
Yeah, so could you give some reference to some books?
I think Shankar talks about these things.
Shankar, okay.
Yeah, Shankar is a pretty good book in terms of, it's a basic book, but it covers all advanced stuff. That's why it's so big.
Okay, thank you, sir.
And I would like you to work out this. These is show. Show that these are the Hamilton's equation that I showed above. I could have made some mistake. I'm writing this down from memory. I didn't include this in my lecture notes. Okay, any other questions?
No, sir.
Anyone else?